Urban metabolism is a concept or tool to quantify resource consumption and material flows in cities, and is visualized graphically to give a good overview of the energy intensity of the activities taking place in cities. Let's put forward some key definitions first and take a look at urban metabolism from its conception, and then look at urban metabolism studies from different parts of the world. Before offering a definition of urban metabolism, I want to define a word we're more familiar with, which is metabolism, just metabolism. Metabolism is the sum total of the chemical processes that occur in living organisms, resulting in growth, production of energy, elimination of waste, etc., as defined in the British Dictionary. You've probably come across metabolism in the context of human metabolism. Our body's metabolism is the sum of the physical and chemical processes in our bodies, by which what we consume as food and water and air, its material substance is produced, maintained, and destroyed through outputs from our bodies, and by which energy is made available for our physical activities and other bodily energy requirements that enable us to breathe, think, move, and allows all our organs to function. It's almost a description of what goes on in our digestive system to ensure we function. Okay, now hold that thought. As it applies to cities, urban metabolism is the sum total of the technical and economic processes that occur in cities, resulting in growth, production of energy, and elimination of waste, as defined by Kennedy et al. It's a description of activities in a city that makes the city function. The origins of urban metabolism span back almost 60 years ago, when an article was published in Scientific American in 1965 by Abel Woolman on the metabolism of cities. The research was motivated by the attention being focused on water shortages and air and water pollution in the United States, yet recognizing that there was plenty of water, but its supply required foresight, and that the pollution caused required the need for economic decisions to be made. A brief about Abel Woolman, the author of The Metabolism of Cities. He lived a long life from 1892 to 1989 and was an American scientist, an engineering professor at Johns Hopkins University, and was considered a pioneer in sanitary engineering, where he combined engineering with public health and hygiene. His work on supplying clean water spanned a productive 8 decades. He was also the one who developed the urban metabolism concept as a method of analyzing cities and communities through quantifying inputs that included water, food, and fuel, and outputs that included sewage, solid waste, and air pollutants, while tracking these flows in the urban setting. Woolman developed the concept, and concerned about deteriorating air and water qualities in American cities, he also developed the first urban metabolism study. In his article in Scientific American, he has an image of the pollution of Lake Erie from the highly industrialized shorelines of Cleveland. This image here that I've chosen shows the Buffalo waterfront and Lake Erie, where the discoloration of the water is actually polluted water flowing into Lake Erie from the Buffalo River. The first urban metabolism study was a model to determine the inflow and outflow rates of a hypothetical American city with a population of 1 million people, which was constructed to visualize flows and be able to respond to metabolic challenges, particularly with regards to water supply management, sewage disposal, and air pollution control. The model allows the monitoring of the natural resources used and the consequential creation and output of waste. We know there are limitations on the natural resources we use on a day-to-day basis, and with frequent use, the creation and accumulation of waste can and will occur and will create problems. In the model, the inflows of water, food, and fuel for the activities of 1 million people are visualized in units of tons per day. On a daily basis, there's 625,000 tons of water, 2,000 tons of food, 9,500 tons of fuel. This is divided into 3,000 tons of coal, 2,800 tons of oil, 2,700 tons of natural gas, and 1,000 tons of motor fuel. Woolman says, and I quote, "Water which enters the city silently and unseen overshadows all other inputs in volume." End of quote. After water is used by the city's residents, it returns to the city's sewers in a contaminated state. The resulting outflows, also measured in units of tons per day, are primarily sewage at 500,000 tons and 120 tons of suspended solids in this sewage. Solid waste, shown here as refuse, coming out to 2,000 tons, and air pollutants at 950 tons, which are divided into 150 tons of particles, 150 tons of sulfur dioxide, 100 tons of nitrogen oxides, 100 tons of hydrocarbons, and 450 tons of carbon monoxide on a daily basis. These air pollutants are largely a result of the combustion of fossil fuels. Following the first urban metabolism study by Woolman of an average hypothetical city in the United States, some of the earlier urban metabolism studies were developed in the 1970s. By way of example, there are studies of Tokyo, Brussels, Hong Kong, Miami, and Paris, and I'll show you what their urban metabolism diagrams look like when they were produced then, focusing less on the actual numbers and more on the variations, which is being captured on the diagrams, and how inflows and outflows are depicted in each one. The urban metabolism of Miami was a result of a study on the energy economic theory and mathematical models for combining the systems of man and nature, with a case study of the urban region of Miami, Florida, published in 1975 by Zucchetto. The data used was data pertaining to natural systems, energy data, and economic data, which were compiled for the Miami-Dade urban region between 1950 and 1972. You can see on the diagram here the city, sort of the big shape in the center, with natural energies flowing in and include the wind, sun, and rain. There's energy, food, and goods shown on the left, and economic inputs on the right. Another flow is external natural land used for the processes within the city. There are lots of elements and activities happening in the city, including transportation, production, water supply, land development, waste processing, private structures, government structures, roads, vehicles, and people. The waste produced includes waste that is processed and that which goes to the oceans, in addition to air pollutants. Next is Tokyo's urban metabolism, published in 1976 by Hanya and Amby as a study on the metabolism of cities in science for a better environment by the Science Council of Japan. Though more straightforward diagram to read, the center is the city, Tokyo, and on the left there's all the inflows into the city, and on the right there's the outflows, both measured in units of billion tons per year, and are generally categorized as flows in the atmosphere, transportation, waterway, and traffic. Taking them in turn, oxygen gas from the atmosphere is an input that comes out as carbon dioxide and water vapor. Goods are transported in and out of the city. Raw water comes into the city and is released as wastewater into rivers and sewers and ocean dumping by ships. And finally, human bodies, referring to traffic, a commuting activity by people in the city. Brussels is next. The urban metabolism study and diagram are published by Duvigneau and Denayer de Smet in 1977 in French. It's a very sophisticated visual that shows lots of details of the flows in and out of the city. Follow the arrows coming in and out, in addition to some of the flows that are outputs that are then fed back into the city. You can see it with water flows. That is, it's a resource that is being reused. The flows quantify people, plants, natural energy, imported energy, which includes food, electricity, carbon, petroleum products, and natural gas. There's also exported energy and exports, which include manufactured products, paper, wood, plastic, plant and animal waste, and glass and iron. In addition, you can also see waste output, and water coming in and water being output as waste and reused once again. Next is the urban metabolism of Paris, which is a 1977 study of the urban agricultural ecosystem of 19th century Paris by Stanhill. You probably already by now can notice some of the similarities among these urban metabolism diagrams. The diagram on the left shows a visual of the flows where the large square is a depiction of the boundaries of the city, and going around the square, starting from the bottom right, the inputs, including the sun, wind, water, fiber, Food for activities in the city that pertain to buildings and assets, people, horses and trees and grass. Outputs include the financial gains from markets, and horse waste, which are nutrients into other processes, such as the making of fertilizer. Turning to the diagram on the right, it shows some relevant quantities as it pertains to the flows of NPK, N for nitrogen, P for phosphorus, and K for potassium. These are the essential components of fertilizer. The focus on these elements is because this particular study had a focus on the urban agricultural component. The circle in the middle is the boundaries of Paris, and the outer circle is a supply chain of horse fodder and bedding coming into the city, which is used in the city and results in horse stable manure and crops and soil. The smaller inner circle within Paris is the Marais of Paris, which is the agricultural area in focus in this study, and shows outputs of crops for export or for reuse or as waste, in addition to outputs of soil. Next is the Urban Metabolism of Hong Kong, which was published by Newcomb and colleagues in 1978. You can see the city skyline as a visual of the city and the surrounding environment. Look at the arrows in and out of the city. Let's follow them around the diagram, starting from the top left. There's inputs of fresh water, cargo, people, seawater, human, food. There's inputs of fresh water, cargo, people, seawater, human food, animal food, liquid fuels, solid fuels, materials including glass, plastics, cement, wood, iron, steel, and paper. And the outputs include refuse of glass, wood, iron, steel, paper, food, plastics, sewage solids, sewage liquids, cargo, and people outputs. And exports including glass, plastics, wood, iron, steel, paper, cement, human food, liquid fuels, and solid fuels, in addition to gases released to the atmosphere, including carbon monoxide, sulfur dioxide, nitrous oxides, hydrocarbons, lead, and particulates. You can actually tell a lot about the city by looking at the nature of the activities and the sources of their energies, and sometimes even these diagrams give insight into the major industries in the city. Now fast forward about 30 years since Abel Woolman's pioneering work, and there's Herbert Girardet, who worked off of Woolman's work and began to see a connection between urban metabolism and the sustainable development of cities. Girardet, born in 1943, is an ecologist, author, a consultant to UNEP, the United Nations Environment Programme, and UN Habitat, and co-founder of the World Future Council, and very much active today publishing about cities and energy. Some of his books include Cities, People, Planet, Urban Development and Climate Change, published in 2004, Surviving the Century, Facing Climate Change and Other Global Challenges, published in 2008, A Renewable World, Energy, Ecology, Equality, published in 2009, and Creating Regenerative Cities, published in 2015. Girardet laid the foundation for the industrial ecology approach to urban metabolism, in which it is seen as the conversion of nature into society. Girardet outlines the difference between circular and linear metabolism, where in a circular cycle, there is nearly no waste and almost everything is reused, a natural world process. What comes in is mostly reused, resulting in very little waste. Whereas on the other hand, a linear metabolism, which is characterized as an urban world process, has a clear resource input and waste output. Insight into linear versus circular flows address questions like, if material and resource flows are not being reused, they are being wasted, and we have limited resources, so how can we best use our natural resources? Or, if material and resource flows are being recycled back and reused in the city, what technologies make that possible? What else can be reused? And how can we close these material flows and create circular flows as much as possible to produce as little waste as possible? Building on the knowledge established for urban metabolism is an extended metabolism model developed by Newman in 1999. It came about as a result of a study of Australia, which identified larger cities as more sustainable in terms of use of resources and livability on a per capita basis, utilizing indicators such as income, education, housing, and accessibility. By the same token, these cities were also more likely to reach unsustainable limits, demonstrating increasing metabolic flows and visible livability deterioration from their core to the outer suburbs. In addition, previously, urban and coastal settlements, which are the least sustainable of all developments, and rural settlements, had the lowest metabolic flows and livability measures. As such, Newman extended the urban metabolism model to address sustainability goals by including the dynamics of settlements and livability in these areas. He defined the physical, biological, and human basis of the city and integrated economic and social aspects of sustainability with the environment. As shown on the diagram, resource inputs are similar to those we've seen earlier in other urban metabolism diagrams such as land, water, food, energy, building materials, and other resource inputs. The dynamics of settlement implies activities of people in cities include things like transportation, economic and cultural priorities, which produce outputs like waste outputs, and we've seen before on other urban metabolism diagrams like solid waste, liquid waste, toxics, sewage, air pollutants, greenhouse gases, waste heat, and noise. And novel here are the livability indicators, which are produced as a result of how the city and its people work, and include health, employment, income, education, housing, leisure activities, accessibility, urban design, quality, and community. Newman applied this extended model of assessing metabolic flows and livability to a range of human activities in industrial areas, households, and neighborhoods, urban demonstration projects, and for city comparisons. Another addition to urban metabolism is the inputs into and outputs out of the anthroposphere that was developed by Hendricks and colleagues in 2000, in which they provide a system-level understanding of how a city, region, or nation functions by looking at inputs and outputs of urban processes and the inputs and outputs of natural processes and the interactions between the two. And one more urban metabolism outlook. Peter Boccini and Paul Brunner co-authored The Metabolism of the Anthroposphere, first in 1991 and again in 2012, in which they take this global network of urban systems, including ecosystems, which is what is referred to as the anthroposphere, and take a closer look at the physical flows and stocks of matter and energy within it that form its metabolism. The second edition of the influential book that has been substantially revised and expanded 20 years later includes an emphasis on design and resource utilization, which reflects recent debates and scholarship on sustainable development and climate change. With these additional advances to urban metabolism, there are many studies that were developed after these earlier ones I just showed and continue to be developed today. I encourage you to visit the website shown in the link, metabolismofcities.org, that takes you to the Metabolism of Cities website, where you can review urban metabolism studies if you click on the Publication Database button, and explore urban metabolism diagrams if you click on the Data button. Go ahead and take some time to visit this wonderful online resource for urban metabolism. For some more excitement, and because I've already shared with you the urban metabolism of 19th century Paris, which is as old as urban metabolisms get, the link below, metabolism.paris.fr, that takes you to an animation of urban metabolism put together by Paris City Hall, where you can see the actual flows, both linear and circular, of materials, energy, and water for the city of Paris and for the larger Île-de-France region for different timelines, which for the time being you can toggle between 2003 and 2014. Unfortunately, it's only available in French, but you'll visualize the flows nonetheless, even without knowledge of French, because the website has representative icons for their flow types and geographic regions. It's clear there are so many variations of what is measured and what is shown on urban metabolism diagrams, and they've generally evolved over time. Kennedy et al., having conducted reviews of urban metabolism, put together a list of recommended components of urban metabolism in their 2011 paper titled The Study of Urban Metabolism and Its Application to Urban Planning and Design. They recommended the following be shown on urban metabolism diagrams. total electricity consumption measured in gigawatt hours, consumption of heating and industrial fuels by each fuel type measured in terajoules for each fuel type and includes, for example, natural gas, fuel oils, coal, liquefied petroleum gas, and includes fuels used in combined heat and power plants. Total consumption of ground transportation fuels like gasoline, diesel, or other, based on sales data and measured in million liters for each fuel type. Volume of jet fuel loaded onto planes at airports within the boundary of the city or urban region measured in million liters. Volume of marine fuel loaded onto vessels at the city's port, if applicable, and measured in million liters. Tonnage measured in tons and composition of landfill waste in percentage terms of food, garden, paper, wood, textiles, industrial, other, or inert waste from all sectors, and percentage of landfill methane that is captured. Tonnage of solid waste incinerated, if applicable, and measured in tons. Masses of steel, cement, and other materials or chemicals produced in the city causing non-energy related industrial process emissions measured in tons. Beyond scientific interest alone in the nature of city growth, there are practical reasons for studying urban metabolism. When looking at the application of urban metabolism, Kennedy et al. Suggests that the potential to use this concept in an urban design context is a relatively new development. Some applications include using material and resource flows from urban metabolism studies as urban sustainability indicators. The quantification of energy flows by fuel type and by sector can be used as inputs into urban greenhouse gas emissions inventory calculations. Mathematical models of urban metabolism can be used to provide evidence-based research to support policy analysis and can be used as a basis for sustainable urban design by reducing resource consumption, reducing waste, minimizing linear flows that are wasteful, and closing material flows. Urban policymakers are encouraged to make sense of the urban metabolism of their cities. It is practical for them to know if they are using water, energy, materials, and nutrients efficiently, and how this compares to that of other cities. They must consider to what extent their local resources are being exhausted, and if necessary, the appropriate strategies to slow or avoid exploitation of resources. And the future of urban metabolism? Well, from a very broad perspective, future directions include a fuller integration of social, health, and economic indicators into the urban metabolism framework, while tackling the great sustainability challenge of reconstructing cities. More specific research needs include work on the relationship between urban metabolism and the urban poor, and efforts to collect and combine energy use data from world cities, and development of a standard classification system for stocks and flows in the urban metabolism, so that city-to-city comparisons can be made possible.